start. So first of all, well, thank you to all the members of the jury for accepting to review my work. And thanks to all of you for being here. So without further ado, I'll start my presentation on the impact of self-segmentation training on medical image segmentation and uncertainty representation. So first of all, what's on the menu for today? So I'll start with a short literature review on deep learning models for segmentation and some issues with them. Then I'll move on to my research objectives and contributions to tackle some of these issues. Then I'll do a discussion on the clinical usefulness, limitations, and perspectives of this work. And I'll finish up with a short conclusion. So segmentation in medical imaging is the delineation of anatomical structures. So here I put two examples of this. So on the left, we have spinal cord gray and white matter segmentation. And on the right, we have brain multiple sclerosis or brain MS lesion segmentation. So why do we do this? So one purpose is to have some volumetric measurements. But also segmentation can help with diagnosis, disease monitoring over time, or treatment planning for surgery, for example. So typically, the segmentations are done manually. However, it's a very long and tedious task. So there's a lot of research done to try to find automated methods to do the segmentation. And one very popular way of doing this is deep learning. So how do we train a deep learning model? Usually to train a neural network like this one, we need pairs of image and manual segmentation. And the manual segmentation is usually binary as the one presented here. So can you see my cursor? Yes, okay, good. So as the one presented here, which is usually binary. So one everywhere there is the tissue of interest and zero in the background. So the image passes through the neural network and the model needs to try to predict for each voxel of the image if the voxel is part of the background or part of the segmentation. So it's really a classification task where each voxel is attributed a value between 0 and 1, but mostly 0 or 1. So we use the loss function to compare the model prediction to the model segmentation. And the loss function tries to minimize the differences between these two and will help to update the weights of the neural network. So the training is really an iterative learning process. So as we can see on this part of the slide, so after only 5 epoch, which means that the model has seen the whole data set 5 times, the prediction is pretty coarse, but the more the model is exposed to the training data, the better the prediction gets. So one way to quantify the quality of our prediction is to use a very popular dice score. So the dice score is twice the overlap between two segmentation over their volume or their area. So if two segmentation overlaps perfectly, then the dice score is 1, which is the optimal value, and the minimal value is of 0. So as I mentioned, usually we have these binary segmentation or binary labels that we consider as ground truth. However, it's not necessarily the best representation of reality. So why is that? So first of all, in medical imaging, we have inter-rater variability. So that means that not all raters will do the segmentation the exact same way. And this can be due to the expert's experience or training, the quality of the image, or the clarity of the guideline to do the segmentation. So here we have one example of brain MS segmentation done by 7 different expert raters. And as we can see on the far right, where we have the average of all these segmentation. So regions that are in blue, usually there's only few of them that have annotated this region. And if it's dark red, then it means that there was a consensus on what was segmented. So what we can see is that there's pretty much a rainbow of colors, and it probably represents a little bit better the reality, because inter-rater disagreement is part of medical imaging. Another thing that we need to take into consideration is the partial volume effect, which is caused by the limited spatial resolution when we do an object acquisition. So for example, if we try to acquire this round object at the resolution described by the gray dashed lines over here, we'll probably get an image that would look something like the second image over here. So when in a single voxel, like this one over here, there is more than one tissue type. So here we can see that there's the background and maybe the tissue of interest. Then the resulting intensity of this voxel is the weighted average of the intensity of these tissues. So if we try to represent this object by a binary segmentation, first of all, it's not doesn't necessarily represent the reality quite well, since, for example, here in the binary representation, this voxel is attributed to background. But if we look at the original image, we can see that there is still a bit of tissue in this voxel. And second of all, it can cause volumetric bias, which means that if we try to measure the volume based on the segmentation, then we have a loss of precision, especially at the boundary of the image. So we have imprecision in the volumetric measurements. So finally, on the far right over here is just an example of what it can look, what partial volume effect can look on real images. So it usually occurs more at tissue boundaries, and we can see different scales of gray. So another problem with modern neural network is that they are most of the time overconfident, which means that they are miscalibrated. So what we would hope is that that the prediction of our neural network or our segmentation model would output values between 0 and 1 that would represent their confidence toward their prediction. So for example, if my model attributes 0.8 or a value of 0.8 to a voxel, I would hope that around 80% of the time this prediction is right. However, in reality, it's usually not the case. So one way to represent or to quantify the calibration is to do a reliability diagram as we see here. So we take all the prediction from the model and we store them into ordinal bins of 0.1, for example. And for each of these bins, we compute, first of all, the accuracy of the voxels. So how many of these voxels were well classified, and we compare this to the confidence of the model, which is the average prediction in this bin. And what we would hope is that the accuracy and the confidence would match. So we want to see white bands that fall very closely to this red dashed line, which represents a perfectly calibrated model. But in most modern neural networks, we have these overconfidence gaps, which means that, for example, we have a prediction of 0.95, which can be considered pretty high. In reality, when we look in this bin, the average accuracy would be around 75, for example. So one way to summarize this reliability diagram into a single number is to use the expected calibration error, or ECE, which we try here to minimize. So here we compare the accuracy and confidence, which we hope would be pretty similar. So that would lead up to a number around 0. And we weight this number by the number of voxel in each bin. So in summary, segmentation is really treated as a classification task using binary labels, and the predictions are often miscalibrated or overconfident. And these binary labels disregard the partial volume information in the image, the inter-rater variability, and the uncertainty representation overall, because a binary label of 0 and 1 cannot contain this information. We would need to have more values between 0 and 1 to have a good uncertainty representation. So a segmentation like the one presented on the far right is probably closer to reality than this binary label. So now I'll talk about some of the related works of other authors to tackle some of these issues. So Mueller and al. Demonstrated that smoothing the classification labels, so instead of using classification labels with only 0 and 1, they tried to smooth, so use values between 0 and 1 to represent their ground truth. And they realized it could reduce the overconfidence of the model and improve the generalization. A similar approach was done for segmentation by Lee and al. And so what they did, they smoothed the boundaries of their ground truth based on the distance to the boundary of their binary ground truth that they had. And in their case, it improved slightly the segmentation performance. Finally, in a context where we have more than one annotation per image from different raters, some authors like Django and al. And Jensen and al. Compared different label fusion methods. And they noticed that when they use no label fusion, so when they use all these annotations without aggregating them into a single label, they had a better uncertainty representation and it improved the calibration. So this leads us to my research objectives. So first, we wanted to present a new approach that would think of segmentation more like a regression task than a classification task. So we can have a model that predicts softer outputs. This way we could reflect the partial volume information, the inter-rater variability, or even ill-defined boundaries. And so the second objective was really to test this new approach and test the quality of these soft predictions to make sure that the softness in our prediction also corresponded to zones where there is high inter-rater variability, for example, or partial volume effect, and to make sure that our overall predictions were calibrated. Finally, the final objective was to implement all these research tools and make them publicly available and open to the community. So now I'll introduce the first article that I will be presenting. So SoftSeg, advantages of soft versus binary training for image segmentation. So we targeted 3 of the main features that we thought were causing some information loss and encouraging the model to output binary labels. And we tried to modify these 3 features so to create a model that would predict softer outputs. So we assessed the qualitative aspect of the segmentation, and of course, we quantify the segmentation performance. And we did this on 3 publicly available data sets that I will be presenting in a further slide. So the first feature that we tackle is the label processing. So before training a neural network, we need usually to pre-process our data to a common resolution and to do some data augmentation to avoid overfitting. So data augmentation is just doing slight modification to the image and its ground truth to make sure that the model doesn't learn by heart all the training examples. So the pre-processing and data augmentation require to do some interpolation. So here, instead of having a binary ground truth, after the pre-processing and data augmentation, we use an interpolation of order 1, or it could be higher, to have a soft ground truth like this one. This way we can avoid some information loss on the object boundary, like over here. So instead of having this binary ground truth, we would have something softer, and basically we just derive the softness from the operation that we have initially done. So the second feature that we modified was the final activation. So to make sure that our final output for the segmentation are between 0 and 1, a sigmoid function is usually applied as last layer of the neural network. So here I present the equation of the sigmoid. So we can see that there is an exponential, and this exponential creates nonlinearity in the overall function. So what that creates is 2 plateaus near leading to values near 0 and values near 1. So if the model predicts very low or very high values, it will automatically be classified as 0 or 1. So this means that we can have a loss in the scale differences when we compare the raw output of the model to the final prediction that we observe. So if the model predicts 10 or 100, which are pretty different numbers, the final output is still 1. So instead, we propose to use the ReLU activation function, but normalize it to make sure that the final output is between 0 and 1. This way, all the positive values output by the model will linearly correlate with the final output as we see. So we keep the scale differences of the raw output model. And all the positive values are usually associated with the segmentation itself. So this is why we only keep the linearity for the positive values. The final feature that we modified is the loss function. So two of the most popular loss functions are cross entropy and the dice loss. Both of them are classification losses, which means that they try to encourage the model to predict either a 0 or a 1. So even if the ground truth is of 0.5, in our ground truth, then the optimal and minimal value of this loss will still be 1. So if my ground truth is of 0.5, I usually want my model to reproduce exactly my ground truth. However, in this case, the model will still try to, the optimal value will still be 1. So instead of using a classification loss, we suggest to use a regression loss. So in that case, if we use a regression loss, when we have a soft ground truth of 0.5, for example, the optimal and minimal value of our loss function will also be this 0.5. So this way, we encourage the model to predict not only 0 or 1, but values in between. So in summary, we modified three key features of the conventional training pipeline. So the first one, the way we pre-process the data. So we use soft ground truth derived from the interpolation of our labels due to data augmentation and pre-processing. Then we change the final activation function to a normalized ReLU instead of a sigmoid. And finally, we use a regression loss function instead of a classification loss, like the dice loss. So these three modifications we will call SoftSeg throughout this presentation. So to evaluate our SoftSeg approach, we use 3 data sets. So the first one is the spinal cord gray matter challenge, which is composed of 80 MRI scans from 80 different patients, and they were acquired from 4 different centers, and they all had different acquisition parameters. The second data set that we use is the brain MS lesion, which was composed of 15 patients. And the last data set that we used is a subset of the brain tumor data set from the BRAT Challenge 2019. So we randomly selected 20 high-grade cases from this data set, and we use the tumor core as a target label. So first of all, when we look at the training progression, so what we can see is that even very early on in the training process, the conventional model output very overconfident prediction. So the prediction is pretty coarse, but most of the values are near 1. That could indicate a high level of confidence. But when we look in counterpart to the SoftSeg model, we can see that already early on in the training progression, the outputs or the predictions are more ambivalent and they're closer to 0, which is normal because the output is still very coarse and it's still very early on in the training process. However, the more the SoftSeg, both model, but especially the SoftSeg model is trained, the more it gains in confidence. And if we look at the last epoch over here, we can see that there is a nice soft boundary around the gray matter, which is expected because it's probably over around these areas that we have more uncertainty. And when we look at the conventional model, pretty similar as what we saw early on in the training process. So most of the predictions are 0 or 1. So if we look at the brain MS lesions, so we can still see this nice softness around the tissue segmentation. But another thing that we have noticed is that the conventional model had a tendency to overlook or not segment some of the smaller or maybe more subtle lesions, while the SoftSeg model had a slightly higher lesion true positive rate, so was able to detect more of these true lesions. So it is true in this example that is shown over here, but it was also true over all the, so we trained 10 models for each of the pipelines, and we had, of course, multiple patients, and in all the tables that I will be presenting, we have the mean plus or minus the standard deviation of these predictions. So overall, the SoftSeg model had a higher lesion true positive rate compared to the conventional. So here, just to summarize quickly some of the segmentation performance. So we did look at a few segmentation performance metrics. Here, I only present, due to lack of time, the very popular DICE score. But overall, on all our data sets and throughout all the models that we have trained, SoftSeg had a higher DICE score compared to the conventional training pipeline. So in conclusion, SoftSeg had the overall best segmentation performance while generating soft predictions. So the next step, we wanted to actually quantify the quality of our soft output. So to verify if the softness in our prediction really corresponds to areas where there might be high inter-rater variability, we wanted to verify that our predictions were calibrated, and maybe also evaluate the correspondence between the softness in our prediction and the partial volume effect. So now I'll introduce the second article that I will be presenting. So label fusion and training methods for reliable representation of inter-rater uncertainty. So in this work, we use only data set that had more than one annotation per image done by different raters. And we wanted to, first of all, compare these different label fusion methods. And we wanted to pair each of them with the conventional or SoftSeg framework to see which performed better. So we assessed the inter-rater variability representation, the calibration, and of course, the segmentation performance. We did this on using two of the data sets that I have just presented. So the spinal cord gray and white matter data set, which is composed of 4 expert raters per image, and the brain MS lesion data set, which is composed of 7 ratings per image. So here is a summary of some of the most popular label fusion methods. However, for this paper, we only focus on 3 of them. So there's like 2 families. So the label fusion methods that generate binary outputs, so only 0 or 1, and the soft fusion methods that will generate labels that have values everywhere from 0 to 1. So the first one that we were interested in, that is probably one of the most popular label fusion method, is staple. So staple is a weighted voting algorithm. So if I have to summarize it, it's kind of a smart majority voting algorithm to take into consideration all of the raters and the annotation that we have. The second label fusion method that we use is the average. So simply averaging all the annotations that we had. And here we assume, or we consider that all the raters had equal experience, and we consider them equally having a regular average. And the last label fusion method, which is actually using no fusion method, was the random sampling. So how it works is that at every epoch of the training, we randomly sample the annotation from one rater randomly. So this way, at the end of the training process, the model will have been exposed to all of the annotations that were available. So here is the summary of the candidate description. So all our columns here represent the label fusion methods, and each of them were paired with the conventional or SoftSeg training framework, which leads us to 6 different candidates. So the first thing we wanted to look at was the uncertainty representation. So one way to measure the uncertainty is to use the entropy. So if the model predicts a model of 0.5, it's probably because it's very ambivalent on whether this voxel should be in the background or in the segmentation. So in that case, we will have a high entropy, which equates to a high uncertainty. And if the model predicts 0 or 1, it's because it's probably very confident that the voxel is in the background or in the segmentation, which will lead to low entropy, meaning that we have also lower uncertainty. So we compare the prediction with the average ground truth. So here in the average ground truth, we have some information about the inter-rater disagreement. So what we would hope here is that the uncertainty from our prediction would match the uncertainty generated from the inter-rater disagreement. So first of all, we looked at the patient-wise uncertainty correspondence. So we wanted to see if the entropy from the prediction would match the entropy of our average ground truth. So to do that, we use the mean absolute error, and we sum that over all of the images that we had. And here we would hope to have a value near 0 because we were hoping that these values would match closely. Then we looked at the voxel-wise uncertainty correspondence. So now instead of looking at the uncertainty on an image-wise metric, we wanted to look at the correspondence between each voxel. So to verify that if there is a zone in my ground truth where there is high inter-rater variability, do I have this same high uncertainty in my prediction? So to do that, we use the Breyer score, which is also a metric that we try to minimize because we want the differences between both segmentation to be minimal. So first of all, we can look at a graph representing the patient-wise uncertainty correspondence. So here are the results only for the brain MS. So the first row represent all the conventional model, and the second row represent all the SoftSeg models. So what we can see is that when we look at the conventional models, and regardless of the label fusion method, the overall entropy of the prediction, which can translate into its uncertainty, is much lower when we compare it to the entropy generated from the inter-rater disagreement of our raters. And what we would hope is that all these data points would fall very near this black dashed line over here, which would represent a perfect match between the prediction and the ground truth. However, when we look at the SoftSeg models, then we can see that these data points fall much closer to this black dashed line. So here, what we can see is that our SoftSeg models represented maybe a little bit more truthfully the uncertainty on a patient-wise level of the inter-rater disagreement compared to the conventional. However, when we look at the label fusion methods, there is no clear consensus on which one would be the best. So now if we look at the matrix from all of our prediction from both data set. So these columns here, MAE and Breyer score, are the metrics that I have introduced in the slide earlier. And one thing that we can see, so both of these metrics will represent the uncertainty correspondence between the prediction and the ground truth. So what we can see is that if we compare SoftSeg to conventional in the pairwise fashion, where we keep the label fusion method constant, all of the time for all the data sets and all the metric, SoftSeg outperform the conventional training framework. However, when we look at the best stable fusion method, there is no clear consensus. So stable was best for the patient-wise uncertainty correspondence, but random sampling was better when we looked at the voxel-wise uncertainty correspondence. So now let's move on to calibration. So we can see pretty similar trends here. So once again, the first row are all the conventional models. The second row are all the SoftSeg models. So if we look at the conventional models, we can see that they all have more or less important overconfidence gap, which is kind of what we expected because we know that neural networks are usually overconfident. And when we look at, so we can see these overconfidence gap, which are these pink rectangles, which is the gap between the actual accuracy and the confidence of the model. And when we compare to the SoftSeg models, we can see that our white bands over here fall much closer to the perfectly calibrated ideal that we had. But there is a slight underconfidence, which means that there might be a little bit slightly too much softness. However, when we look at the expected calibration error or ECE presented over here, the ECE falls pretty close to 0, and it's much lower compared to the ECE we had for the conventional models. So what we can conclude here is that the SoftSeg models had more calibrated outputs. And once again, we do not see a clear winner in terms of label fusion method. So to conclude the results section of the second article, I will talk about the segmentation performance. So we did look at multiple segmentation performance metrics, but here we try to summarize all of these into a composite score. So the composite score aggregates the dice, the precision, recall, and absolute volume difference. And all of these metrics were standardized to a mean of 0 and standard deviation of 1 to be able to aggregate them. So here for both data set, all of the candidates are sorted from best to worst composite from best to worst mean composite score. So the first one had the best average. So the best candidate for the spinal cord gray and white matter segmentation was the SoftSeg staple. And what we can see, once again, if we do a pairwise comparison between the stable and conventional models, we always have the SoftSeg outperforming the conventional. However, when we look at the brain MS, so here the best candidate was SoftSeg average. However, there was no statistical difference between this candidate and the conventional staple. However, we can see that at least the segmentation performance was similar to the conventional. So overall, if we look at both data set, the segmentation performance was similar or even higher depending on what task we're looking at. So in conclusion, SoftSeg candidates compared with their conventional counterparts had a better inter-rater uncertainty representation, had better calibrated outputs, and had similar or higher segmentation performance. So we could not see a clear winner in terms of the best stable fusion method. However, SoftSeg did most of the time outperform the conventional training pipeline for a segmentation model. So this brings us to the discussion of my presentation. So why do we want to have, or why is it useful to have soft segmentation prediction? So first of all, it can help, as I mentioned throughout my presentation, with inter-rater and uncertainty representation in general. So in a clinical setting, we do not have the ground truth of our predictions. So it's really hard to tell if a prediction is good or bad, or just to know in general, if our prediction is good. So the uncertainty can be a good proxy to the segmentation quality. So usually predictions that are more uncertain are more likely to be wrong. So as we can see on this graph, which is derived from the results from the brain MS model, we can see that there is a good correlation between the predicted entropy or the uncertainty of the model and the MSE here, which is the mean square error between the ground truth and the prediction, which is essentially a segmentation quality metric. So all of the images that had the highest uncertainty also had the worst MSE. So all these images or prediction could be referred to an expert and reviewed by a human because they are more likely to be wrong. A second advantage is the potential mitigation of the volumetric bias when we do volumetric measurements, because soft prediction can take into account the partial volume effect, whereas a binary output do not do that. Then we have the possibility of encoding soft labels. So for example, a rater that is uncertain about an MS lesion segmentation, so instead of having to make a decision between 0 and 1, could annotate it with a 0.5, for example. And we could use that in the SoftSeg training framework. And finally, as I have presented in the 2 other articles, there is also a potential to increase the segmentation performance depending on what task we're looking at. So some limitation of this work. So we only use small or limited size data set. So in all the data sets that we have used, there was only a few patients, so from 15 to 80 patients, and we only use an MRI data set. So it would be interesting to test a SoftSeg on other larger medical data sets or other medical modalities like CT scans, for example, or even in non-medical imaging settings, just to see if SoftSeg could generalize in this context. Then we did not do a thorough evaluation of the volumetric accuracy of our prediction. So to do this and to see if our predictions correlate with the partial volume effect, what would be interesting is to have a data set where we know the actual volume of our object, or use an existing data set and use methods to estimate the partial volume effect. Then there is a lot of things that could be done to optimize the SoftSeg framework. So we did try one combination, but it could be optimized for the use of soft labels or test other regression losses. So we have only tested one. So in conclusion, a soft approach to segmentation tasks demonstrated to help with the uncertainty representation with equal or even superior segmentation performance. So the last objective of my master's was to make our research tools publicly available, which I have done through my contribution to the EvaDomain framework, which is our deep learning toolbox that we developed in the lab. And it's the framework that helps us to train our deep learning models from data loading to data processing to result analyzing and model training. So unfortunately, due to the limited space and time, so I could not include all of the contributions that I did in the past 2 years. But here is a glimpse of some submitted or published work that I have done either here at NeuroPoly or with the Martineau's team back in Boston. And I want to finish this presentation by, first of all, warmly thanking Julien for being my supervisor for the past 2 years. So I had a great experience in the lab, and you were a great mentor to me and really helped me grow as a researcher. So I really want to thank you for that. I also want to do a very special thanks to Charlie, which was there from my first day and is still here today at night in Australia to watch my presentation. So you were a great friend, confident, and mentor throughout all this experience. So I really want to thank you for that. I'm also very grateful for all my friends, colleagues, and collaborators from NeuroPoly, and notably Joseph, Paul Cohen, who helped me with his expertise and AI to elevate my work. So I want to thank him for that. Also, of course, thank you to all my family and friends for supporting me in the past 2 years in this adventure. And of course, thank you to all the funding sources who helped me live for the past 2 years. So now I'm ready for the round of questions and to go deeper into some aspect that I might have gone over quickly. So thank you for your attention.